Say I've got two Go routines I need to sync up after some concurrent work has been done. The easiest way to do this is to just send a message from one to the other over a channel. But I'm only sending that message to force synchronization. What I'm sending isn't that important. What's the smallest possible message that I can send? In other words, what is Go's smallest type? We can explore this question using unsafe.sizeof. Now, the sizeof function isn't completely accurate in every case, and some of what it returns won't be portable between architectures, but it's accurate enough for us to begin our investigation. All we have to do is create a new zero value of some type and then pass that zero value into sizeof. So, for example, if we pass in an int, we get 8 back, and that's because I'm on a 64-bit system. If I were running 32-bit, I would get 4 back. If I check the size of a byte, no surprise, it's 1. A byte is indeed a byte everywhere. But we can do better, right? A bool should only be 1 bit of data. You only need 1 bit to store true or false. So if we check the size of a bool, it's still a byte. And that's not a consequence of sizeof measuring in bytes and rounding up. A bool legitimately takes up 8 bits of data. It turns out you can't have a type that's a fractional number of bytes. And this surprised me the first time I learned it, but the reason why actually makes a lot of sense. It's because types have to be addressable. In other words, they have to be something you can take a pointer of. Pointers literally point to someplace in the program's address space, and that offset is measured in bytes. You can't store a bit offset to a piece of data, so yeah, even a bool takes up an entire byte. But what about something that, in theory, shouldn't take up any space at all, like a struct with nothing in it? Well, according to sizeof, an empty struct is 0 bytes. And don't just take sizeof's word for it. Even according to the Go spec, a struct or array type has size 0 if it contains no fields or elements, respectively, that have a size greater than 0. And we can confirm this. If I print out a 0-sized array of something, its size is also 0. If I print out a 1,000-sized array of empty structs, its size is also 0. Which makes sense, of course. 1,000 of nothing should still be nothing, but how does this work? Well, the key is in the next sentence of the Go spec. 2 distinct 0-sized variables may have the same address in memory. And by printing out the pointer address of each of these values, we can verify that this is true. Since all of these empty values share the same space in memory, the values themselves avoid taking up any additional memory. So what's at this address? Well, let's build an application that uses an empty struct and have a look at its symbol table. If we search the output, we'll find that our empty struct shares its address with this symbol, runtime.0base. This value is the base address for all 0-byte allocations. So everything that you can declare that takes up 0 size should end up pointing to this value. Internally, whenever Go is requested to allocate something of 0 size, the malloc gc function in the runtime will forcibly return you a pointer to this 0 base. Not only does this convention save space, it also provides a useful optimization. Memory allocation isn't a free action, and trying to allocate a 0-sized thing is pretty obviously a waste of time and resources, so the fact that the runtime takes this shortcut has tangible performance benefits. While there are many things that you could declare that should be 0-sized, a common idiom is to use an empty struct to represent a generic 0-sized thing. It's idiomatic in part because that's what's most frequently used, and that's just how idioms work, but I think there's a logical aspect to it too. An array or slice could also be 0-sized, but declaring them demands that you also declare what it's an array or slice of, even though it won't actually store any of those things. A 0-sized struct, on the other hand, is just a struct. It requires no additional information to declare. So what can we do with nothing? To start off, we can build a whole new data structure. Well, okay, it's actually just a special case of an existing data structure, as we'll see, but something that you may have noticed if you're coming to Go from another language is that Go is missing a native set type. At first, this might seem like a weird omission, like sets are actually really useful when you're writing lots of different programs. But Go does have sets. They're maps. In fact, it's likely that every set that you've ever interacted with in any other language was also secretly a map. Think about it. What is a map? It's an unordered collection of unique keys, each of which maps, hence the name, to some corresponding value. But what's a set? Well, it's an unordered collection of unique values. Unique unordered keys, unique unordered values, these are pretty suspiciously similar things. So we could just store those values as keys in a map. The only catch is that we don't want those keys pointing or mapping to any significant values. We're not interested in their values at all, they just have to exist. So you can probably guess what's coming. If we create a map of type T, any type that's comparable, to an empty struct, we've created a set. We can do all the things with this type that we could do with a normal native set type too. We can add things to it by setting their keys to a new empty struct. We could remove things from it by calling the built-in delete function on the map at the thing that we want to remove. And we can test whether something is in the set by using the "OK" idiom. The second value assigned from a map access will be a bool telling you whether the key is present or absent regardless of that key's value. And finally, iterating over everything in the set is just as easy as ranging over the map keys and ignoring their values because, of course, they're nothing interesting. There are, of course, plenty of packages out there that will let you do normal set operations that you may be familiar with from other languages, stuff like unions and intersections and differences and all those sorts of things. But if all you need to do is store and retrieve unique values, then in my opinion, it doesn't make sense to pull in an entire other import when you could just declare a map of t to empty struct and treat it just like you would any other map. We can also return to our initial example now, and you can see that this works just fine with the empty struct acting as our smallest possible message. There's actually another way to express this idea too. If you know that your channel is only going to send one signal, you can actually close it instead of sending information down it. Closing a channel also forces synchronization between Go routines and will immediately unblock any reads from all the other Go routines. This is a really handy thing to do if you've got many Go routines waiting for some action to complete. And by the way, this is actually how context cancellation works under the hood too. But even when you choose to use closing as your signal, it's still useful to declare that initial channel as being a chan of empty struct. This indicates to the reader that no data of interest should be expected to be sent through this channel, and it probably saves an allocation somewhere, but I'm not enough of an expert in the Go runtime to know that for sure. And there are other uses for zero-sized things too. For example, if you need to declare a type that doesn't contain any data but needs to have a method set, say if you need something simple that needs to fulfill an interface, using the empty struct as the underlying type of that new type is the most memory efficient way of doing this. There was also a package that took advantage of zero-sized things to provide something to range over that only takes up a constant amount of memory. It's github.com/bradfitch/iter, and you shouldn't use this package. Like, you really don't need this. Get with the times. We've had range over ints since way back in Go 122, but it was a cute idea. Even though that usage is admittedly pretty silly, I really like that zero-sized values are in the language, and I like how well they compose with other aspects of Go. Without zero-sized values, we would need sets and signals to be defined explicitly rather than emerging as natural interactions between existing features. Anyway, I hope you enjoyed this talk about literally nothing. Leave a like if you learned something. Links to my Discord, Patreon, and other things are on the screen and also in the description down below. Thanks for watching, and I'll see you in the next one.